these are the integrated rate laws that you're going to use in AP Chemistry. You get these two equations on the sheet that you get to use in every test. This applies to first order only, this applies to second order, and this one for third. And what they're doing in every case is they're relating the concentration you have after a certain amount of time is passing with the initial concentration and your K constant. So we know every reaction has a K constant. That K relates the concentration and the rate of that reaction at a certain temperature. So that's the K constant. So as long as you know that, and if you know your initial concentration, you can figure out how much concentration you'd have left afterwards at any given time. So I could plug in 1 minute, 2 minutes, 3, whatever I want to do, and I can find out whatever concentration. So you can use the rest of these variables to solve for any one of them. So if you have your initial, and then whatever concentration you have after a certain amount of time went by, you could also use that to figure out the K. Let's try one. So sucrose decomposes to simpler sugars. The rate of disappearance of sucrose is equal to K times the concentration of sucrose. I can see that this is first order because the rate is equal to K times the concentration. So there's a 1 here that's not written, because anything raised to 1 is just going to be itself. If it were a 0 up here, this would just be rate equals K. And if it were squared, well, we'd see it. We're given the K, so I know I'm going to use the first order equation. I'm going to use this one, natural log of the concentration after time has gone by, minus the natural log of the initial concentration equals negative K constant times T. And I'm solving for T, so I'm going to solve for time. I'll plug in everything and I'll have that T by itself. So that was the natural log of your concentration after time had gone by, and that was 0.001 minus the natural log of the initial concentration, 0.01, divided by that negative K. This way I will get, negative K, I'll get that T alone, and since K was 0.21, I'll have a negative 0.21 per hour. And that will have me solve for the time. There's this little trick when you're doing one natural log minus another one. You can just type that in. That's fine. You can just go natural log of this, get the difference if you'd like. You can also say that this will be equal to the natural log of this divided by this. So I'm going to do that one. This divided by this is 0.1. So I'm going to natural log 0.1. So I just go natural log 0.1. That's it. And I'm going to get negative 2.3 over this negative 0.21, right? And that's per hour. So divided by 0.21, and it's negative. And I get 11 hours. So don't worry about the natural log. Literally all you have to do is hit natural log and then whatever you want to take the natural log of and enter. Very easy. Okay, so that means after 11 hours, this would have dropped down to 90% of its original concentration. The other way that the integrated rate laws can be used is they can all be rearranged into the y equals mx plus b format, or a linear equation. So if you rearrange it to represent a straight line, you'll know what versus what your x is going to be, what your y going to be, and that'll tell you what versus what you can plot for first order or second order or zero order and get a straight line. So if you had a bunch of data, you would know if you're going to plot concentration versus time, 1 over concentration versus time, or natural log of concentration over time to get a straight line. And if you get that straight line, then you know, hey, I've got a first order because I plotted these. So let's see what we would plot. First, we want to get it into the y equals mx plus b. My x is always time, because that's going to be my independent variable. So this is actually going to be my mx, because this guy is kind of my slope. It's a constant, and that's going to be my x. Plus b, so b is the y-intercept. That's the thing that I'm going to have that's not going to change. So this isn't going to change. I'm going to just go ahead and add natural log of the initial concentration to both sides. By the way, this 0 means time 0. That's why I keep saying initial. So my y equals mx plus b format is the natural log of the concentration at some time t is equal to, so this is y, is equal to negative kt plus natural log of my initial concentration at time 0. So this is my m, this is my x, and this is my b. So if I were to plot, if I had a first order reaction and I plotted natural log of the concentration versus time, then I would get a slope that would be equal to negative k. And let's see, I would have an intercept that's going to be equal to 0. So I would have something going like that. Okay? And then this would be equal to negative k, whatever that slope is. For the next one, so let's rearrange this guy. Same thing, t is going to be my x because I'm going to have that as my independent variable. This initial is not going to change. So let's just go ahead and add 1 over the initial concentration of both sides. So then I have 1 over my concentration at whatever time is equal to the k constant times time plus 1 over, oops, I'm going to do the same kind of 1 over that initial concentration. Okay, so again, this is going to be my y equals mx plus b format. So if I were to plot a second order, because this is the second order integrated rate law, if I were to plot for a second order reaction, 1 over concentration as my y versus time, then I would get something looking like this. I made this one negative because I have the negative k. I'm going to make this one positive. I have a positive k. And I would get this straight line starting at some intercept that would be equal to this. Okay, so if I had a reaction and I went ahead and I tried plotting this and I didn't get a straight line, I would know it's not first order. I try again and I try plotting 1 over concentration versus time. If I get a straight line, it's a second order. So the other option is it could be a 0 order. Since this equation isn't given to you on your sheet, I went ahead and wrote it in the y equals mx plus b format. So this is telling you the concentration you have is going to be whatever your initial concentration was minus the rate at which you're losing that concentration, that k constant relating concentration and time, times how much time has gone by. So for this one, it's already in the format we need. So we know if we have a 0 order, we can just plot concentration versus time, and you're going to have the slope that is equal to negative k.